Hello everyone, my name is Satish Appakutan. Today we are going to discuss about trainable quantization methods in deep neural networks. We all know that model quantization is widely used techniques to compress and accelerate deep neural networks. Quantization improves the area efficiency and energy, which aids hardware acceleration. So we will discuss about difficulties of conventional quantization methods, and then we'll try to review two of the papers in advanced quantization methods, which improves the quantization accuracy as well as models, reduce the model size and area. So today's agenda is we will discuss the limitations of conventional quantization approaches. We will review the papers that have a quantization approaches for high accuracy, area, timing, and energy efficiency. Those are hardware-aware automatic quantization with mixed precision and trained ternary quantization. So these are actually a trainable quantization method than manually fixing the word length for each layers during our normal quantization method. We will also go through the results on different network based on these two papers, and we'll end the presentation with a summary. So what are the shortcomings of our traditional or naive quantization method, which we have tried in our project too? We all know that it required domain expertise to explore the vast design space by trading off the accuracy, energy, timing, and model size to find the optimum bit length for each of the layers. So if you have different models with n layers and different hardware platforms, the solutions exist is enormous. And the conventional quantization method also ignores different hardware architectures and quantize all the layers in a uniform way by selecting a same word length for all of the layers. And also it is difficult to retain the accuracy similar to that of a full precision models, and it cannot generalize from one model to another model. How do we solve these problems? So that's where let's review this paper, hardware-aware automated quantization with the mixed precision. The main idea in this paper is that all the layer having a same word length for quantization, always not necessarily to give a better performance in terms of accuracy. And also the quantization policies for different hardware architecture may be different, or it cannot. The one quantization policy may not be optimal for a particular architecture. Let's take a look at these two ideas by going through the plots on the left side here. The mixed precision for different layers is shown in yellow dots, and the curve shows that the accuracy is well above the quantization using a fixed bit 8-bit quantization for the same model mobile net. The reason is that different layers have a different redundancy and have a different arithmetic intensity on the hardware, which advocates for using mixed precision for different layers. Now let's look at this table where the inference is done on a mobile net hardware with 3 different hardware architecture. The architecture 1 is a bit fusion, and architecture 2 is a bit serial matrix operation, in an edge accelerator, and then hardware 3 is a bit serial matrix operation in a cloud accelerator. We can see that the latency on hardware 1 for the best optimal policy are not same for hardware 2 and hardware 3. Similarly, for other quantization policy. Again, coming back to the main ideas of this paper. So the paper actually introduced an automated framework for quantization. It doesn't require domain experts and rule-based heuristics to come up with a quantization. And it is hardware aware because during the quantization framework, the hardware architecture is looped into so that it can reduce area, energy, and latency and storage while doing the quantization. It comes up with a specialized quantization for different hardware architectures, and it also brings the design insights by taking both the computation and memory access into account. So what's the approach in this paper? The main idea is that the quantization model or quantization task is modeled as a reinforcement learning problem. We all know that reinforcement learning is another form of machine learning approach, similar to in another category of machine learning, like supervised learning, unsupervised learning, and then the third category may be reinforcement learning. A basic overview of the reinforcement learning diagram and its approach is shown on the right side of the slide, which have an agent and an environment. The agent acts based on environment's feedback like reward and observation, and agent perform an action based on the feedback or the reward. So the hardware aware quantization method proposed in this paper modeled the quantization task as a reinforcement problem. So the algorithm is described as the RL agent decides bit width of a given neural network in layer-wise manner. Then for each layer, agent receives the layer configuration and statistic as an observation. It outputs the action, which is the bit width of weights and activation. We then leverages the hardware accelerator as the environment to obtain the feedback from hardware to guide the RL agent to satisfy the resource constraints. Here, the hardware accelerator is feedbacks the resource constraints like energy, area, and latency. After all layers are quantized, we fine-tune the quantized model for one more epoch and feed the validation accuracy after short-term retraining as a reward signal to the RL agent. The RL agent is used. The RL agent used is a deep deterministic policy gradient to supervise the RL agent. So overview of the framework they have designed is shown here. We leverage the reinforcement learning to automatically search over the huge quantization design space with hardware in the loop. The agent proposes an optimal bit width allocation policy given the amount of computation resources, that is latency, power, and model size. Our agent integrates the hardware accelerator into the exploration loop so that it can obtain the direct feedback from the hardware instead of relying on indirect proxy signals. So here you can see that actor critic agent is the DDPG model. So how is the RL formulation as done? The state space is defined as an 10-dimensional feature vector, OK as an observation, where OK is actually equal to the K is the kth layer, C in and C out are the channel in and channel out, S kernel is the kernel size, stride, and S feature is the input feature maps, and n params are number of parameters, and binary indicator for the depth-wise, and binary indicator for the weights and activation. and AK-1 is the previous state action. And if it is a fully connected layer, the state space is defined as below, which is here. The only difference is that H in and H out are the number of input neurons, and number of H out is the number of output neurons. The action space, we use a action space determine the bit width. We use a continuous action space which approximate the kth layers bit map with the following equation, where B min and B max are the minimum and maximum bit width for that particular quantization policy. We take the direct feedback from hardware accelerators, so that latency and energy feedbacks are from the hardware, fed back to the RL environment. Quantization, we use a linearly quantize the weight and activation for each layer using an action AK based on the following equation: quantize WAKC with a round clamp WC divided by S into S, and then optimize the vector C with the following equation. So reward function, as we already imposed the constraint on latency, energy for limiting action space, we defined the reward function is related to the accuracy. So every time once the quantization, one time of quantization is completed, one epoch is completed, the reward will be calculated and sent back to the agent for feedback. For the RL agent, we leverage the deep deterministic policy gradient, which is an off-policy actor-critic algorithm for continuous control problem. We apply a variant of form Bellman's equation, where each transition is an episode is defined by the following equation. Exploration. Optimization of the TDPG agent is carried out using ADAM with beta 1 and beta 2. We use fixed learning rate of 10 raised to minus 4 for active network and 10 raised to minus 3 for critic network. During exploration, we employ the following stochastic process and fine-tuning. Once after the exploration, we fine-tune the quantized model for one epoch to help recover the performance, or train the network to get a better performance and accuracy. And we used SGT with a fixed learning rate and a momentum of 0.9. So with that setup, we formulated the quantization policies and done an experiments on MobileNet and MobileNet V2 as an edge accelerator and cloud accelerator, and the comparison is shown in this slide. Here, the latency constraint quantization of bit serial matrix operation, edge accelerator, and cloud accelerator on a MageNet. We can see that the framework can reduce the latency by 1.4 times to 1.95 times with a negligible loss of accuracy compared with the fixed bit width, which is 8-bit quantization. It can be also shown that from the figure 3 that the quantization policy under latency constraint for MobileNet V1 on edge accelerator, our RL agent allocates less activation bits to the depth-wise convolutions, which echoes that the depth-wise convolution are memory bounded and the activation dominates the memory access. On cloud accelerator, our agent allocates more bits to the depth-wise convolution and allocates less bits to the point-wise convolution. As a cloud device has more memory bandwidth and high parallelism, the network appears to be computation bounded. Similarly, quantization policy under latency constraints for MobileNet V2 on BISMO architecture is shown here. Depth-wise layer is assigned with fewer bits on the edge accelerator for the same reason, and point-wise layer is assigned with fewer bits on the cloud accelerator. Latency constraint quantization on bit width is shown here on this table 4. Our framework can reduce the latency by 2 times with almost no loss of accuracy compared to with the fixed bit width 8-bit optimization. On table 5, energy constraint quantization on bit fusion MobileNet V1 on ImageNet, our framework reduces the power consumption by 2 times with nearly no loss of accuracy compared with the fixed bit width quantization. The model size constraint quantization on ImageNet is shown here. Compared with the deep compression, our framework achieves higher accuracy under similar model size, especially under high compression ratio. We can see that from MobileNet, it can go up to 57.14, 81.84, and the model size has significantly reduced to 1.09 MP for MobileNet V1 for compared to 2-bit compression. Similarly, MobileNet V2, which went to 66.75 and 87.32, and with a model size of only 0.95 MP compared to 13.37 MP of original model. Quantization policy under model size constraint for MobileNet V2, our real reinforcement learning agent allocates more bits to the depth-wise convolution, since depth-wise convolution have fewer number of parameters. You can see that from the plot on figure 5. Yeah. So that being some of the features and advantages of hardware-aware quantization method, which we discussed from the paper 1. Now let's look at the second paper, which is a trained ternary quantization method, and we will go through some of the salient features or what is done to gain higher accuracy without taking more area or energy. So let's discuss the related work that leads to ternary quantization method. So Lin et al. Proposed a binary and ternary connection to compress a neural network, which is a binary neural network. They use probability methods to convert a 32-bit weight into binary values, as shown below in the equations. And see here, I have shown a picture of what is the binarization of the weights, where the weights was initially, weight included in the real numbers, and once it is mapped into binary values, the values can be either -1 or 1. So that way we actually reduce no multiplication required once the converted into the real values into the binary values. DoReFaNet, Zhu et al. Proposed DoReFaNet, which quantizes weights, activation, and gradients of neural network using different bit width. They introduced simple quantization method to convert the 32-bit weights into binary values using the following equations. Ternary weight networks. Lee and Leo proposed the ternary weight networks, which reduces accuracy loss of binary networks by introducing 0 as the third quantized value, and hence the name ternary. So instead of you have 3 values to be quantized into it. They use symmetric threshold and a scaling factor WL for each layer, L to quantize weight into minus WL, 0, and WL, as shown in the equation 4. Then solve an optimization problem of minimizing L2 distance between full precision and ternary weights to obtain layer-wise values of WL and WL delta L, as shown. Deep compression. Han et al. Proposed deep compression to prune away trivial connections and reduce precision of weights. In deep compression, low precision weights are fine-tuned from a pre-trained full precision network, and the assignment of such weight is established at the beginning and stay unchanged, while representative value of each cluster is updated throughout fine-tuning. So what is TTQ method? The algorithm is shown here. Normalize the weights in the range of -1 + 1 Organize the intermediate full precision weight to -1, 0, +1 by thresholding. The threshold factor T is a hyperparameter. Perform trained quantization by backpropagating two gradients as shown in the dashed line in the figure, as shown here in the figure. Backpropagate gradient 1 to the full resolution weights and gradient to the scaling coefficient, like this. To learn the ternary values, we introduce two quantization factors, WP and WL, for positive and negative weights in each layer. Feed-forward ternary weights WT is defined as equation 6. Unlike previous work, where quantized weights are calculated from 32-bit weights, the scaling coefficient are two independent parameters and are trained together with the other parameters. Following the rule gradient descent, derivatives of WP and WN are calculated as equation 7, and then we apply these derivative to calculate the loss gradient. We use scale gradients for 32-bit weights. Method continued. The evolution of the ternary weight from different layers during training is shown in figure 2. Here, the ternary weights value above and distribution below with iteration for different layers of ResNet 20 on CFAR 10 is shown. So here the distribution of the ternary values are shown. It is first we approximate to 1 and -1 and 0, and then how it approaches different learned values are shown, catching up, and the distribution of the weights and for different layers are shown in the figure. We can see that it is actually going in this fashion. So the quantization heuristic is that use the maximum absolute value of weights as a reference to the layer threshold and maintain a constant factor T for all layers, as shown in the equation 9. Maintain a constant sparsity R for all layers throughout the training. By adjusting the hyperparameter R, we are able to obtain ternary weight networks with various sparsities. Use the first method and to set T to 0.05 in experiments on CFAR 10 and ImageNet dataset, and second one for wider range of datasets. So now coming to the experiments on or the model evaluation after quantization using CFAR 10 and ImageNet. The following picture shows the result of our quantized model, trained ternary quantization against full precision and binary weight models. We can see that the trained ternary weight, which is a red plot, is actually meeting the full precision one towards when the epochs are higher. So the full precision is shown as a blue. And error rates for full precision and ternary resonates on CFAR 10 is shown in this table. We can see that it is almost matching the full precision, and for ResNet 56, it improves by 0.36 36%. Yeah, error rate is increased by a high percentage actually. Experiments on AlexNet and ImageNet is shown in this table. We can see that again it closely matches with the DoreFaNet and full precision models, and the top one and top 5 error rate for error rate on AlexNet and ImageNet is actually closely matched to the full precision using ternary quantization method. Similarly, top one on ResNet 18 is actually is slightly worse by like a 3%, but it has been much better compared to 1-bit and 2-bit binary and ternary quantization. So performance analysis of a TTQ model. TTQ is a ternary trained quantization. The spatial and energy efficiency, we save storage for models by almost 16x by using ternary weights. Although switching from a binary weight network to ternary weight network increases bits per weight, it brings sparsity to the weights, which gives potential to skip the computation on zero weight and achieve higher energy efficiency. Trade-off between sparsity and accuracy is shown in the plot below. As the sparsity of weights grows from 0 to 0.5, both the training and validation error decreases. Increasing sparsity beyond 50% reduces this model capacity too far. Increasing minimum error occurs with a sparsity between 30% and 50%, which can be shown in this plot. Sparsity and efficiency of AlexNet. AlexNet layer-wise density complement of sparsity as shown in table 4. You can see all the densities and how it got reduced. You can see that the density on the hardcon 1 is 100%, and then the remaining is actually 2-bit, 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 and then the final layer is also used the full precision, and all others are reduced to almost 5 times. Yeah, 5 times. You can see that kernel visualization on the right figure. The left matrix is the left one is a kernels from the second convolution layer, which is a 5 by 5, and the right one is from the third. We pick first 10 input channel and first 10 output channel to display for each layer. Gray, black, and white color represent 0, negative, and positive weights respectively. So here that you only use the first 10 input channel and then first output channel to visualize the kernels. So let's move on to now the comparison. Do we have anything common between these two, or is one method is better than the other one? I reviewed both papers thoroughly, and unfortunately, there is no common database and common data set or model based on which they reported the quantized accuracy. So there is no direct comparison to determine which one is better. The few observations are TTQ uses mainly CFAR10 dataset and ResNet models, and for ImageNet on AlexNet and ResNet 18. For evaluation, the hardware-aware quantization method uses ImageNet on MobileNet and ResNet 50. One observation is that for some models, the TTQ gives better accuracy than corresponding full precision models. The advantage of hardware-aware quantization is that it's completely automated and it doesn't need any domain expert to find the optimal quantization methods or word length. So conclusion, we analyzed two learnable quantization methods, HAQ and TTQ. It can be observed that learnable quantization have higher accuracy than the conventional quantization methods from the result provided. Hardware-aware quantization is an automated framework for quantization which does not require any domain expert and rule-based heuristic, and gives an optimal specialized quantization solution for different hardware platforms. When deploying the ternary network, only the ternary weights and scaling coefficients are needed, which are reducing parameter size by at least 16. Experiment shows that our model reaches or even surpasses the accuracy of full precision models on both CFAR10 and ImageNet dataset. On ImageNet dataset, we exceed the accuracy of prior ternary networks by 3%. With that, I would like to conclude my presentation. Thank you for listening. And if you have any questions, please email to me using the email ID I have provided in the introductory page of the slide. Thank you very much.